Okay. All right. Here we go. We're going to continue with our book review. What is the electron? Right. Volodimir Simulik. We had just finished last video, and by the way, now I think that what I'm doing is I'm going to be uploading directly to library on the app, because then I think at that point I can make a video as long as I want if I use the app instead. If I'm limited to just their capturing off of YouTube, then I can only make about an hour-long video. So I'm going to just wing it, and I'll put this all on YouTube and library. I don't really have any other. I mean, it's at this point I don't really. Maybe eventually I'll start finding some other, like, you know, put it on Facebook or something like that too. But right now, let's get back. Let's get into the book. Okay, the idea here is a survey of competing electron papers and theories. And the idea is to maybe get a better ontological understanding rather than just simply, you know, mathematical. You know, and the funny thing is, though, the author's paper, Volodimir Simulik, his paper actually is not all that ontologically illuminating. He's called the electron as a system of classical electromagnetic and scalar fields, and he actually resorts to sort of a mathematical trick to bring about his model. And the thing is, so his model's not really adding anything to an ontological understanding. That is, you know, understanding the nature of the mechanism. Now, the whole problem with understanding electron is that if it's extended in space, if it's not a point particle, then the idea is that it would be impossible for it not to self-repel and explode. And so that's why a lot of these theories have been based on point particle. But then if you have a point particle, you can't get angular momentum and magnetic moments and the various other properties that require an extension in space. If I recall correctly, this last model here, this electron is a system of classical electromagnetic scale. I think what he did was start out with the Hamiltonian, and then when he got to a certain point, he plugged in the Lagrangian to get the things like angular momentum and so forth. And I once got in trouble. Somebody like got their nappies all in a twist because I had used epistemic instead of ontic. And but my understanding is, okay, if you have a understanding of the ontic, the ontology understood, then you get your epistemology thrown in, because my understanding is that if the way we know things is by understanding, in a sense, an understanding of the mechanical process, and therefore if you have your ontology all in a row, then your epistemology comes in for free. You know, they're integrated like that. So that's the way I use these terms. I I'm suggesting that's epistemology. The bottom line is having your ontology correct, and epistemology is fulfilled in the process. It's a given. So we're going to go to the next. We're on page 129, and it's called "What Causes the Electron to Weigh?" Malcolm McGregor, Santa Cruz, California. In his book on Albert Einstein entitled "Subtle is the Lord," which was published in 1982, Abraham Paas had a selection called Electromagnetic Mass, the First Century. The last two sentences in this section summarize his conclusions. Recently, unified field theories has taught us that the mass of the electron is certainly not purely electromagnetic in nature, but we still do not know what caused the electron to weigh. In the present article, we discuss various ideas that bear on this problem. Recent discoveries in physics have sharpened our interest, but have not yet provided answers. The concept of mass in physics. Our ideas about the concept of mass have gone through several stages of development in the past few centuries, and in particular in the past few decades. During this period, our ability to observe masses, or at least the effect of masses, has dramatically increased, both in the very small scale of the atom and the very large scale of the universe. In the 17th through the 19th centuries, our knowledge of masses seemed to be in pretty good shape. The Newtonian laws of motion delineated the inertial properties of massive objects, and the experiments of Eötvös demonstrated that the gravitational mass is the same as the inertial mass. Physicists didn't worry about the way the mass is distributed in elementary particles or atoms because there was no way of observing them, and there was no clear proof that they even existed. Okay, astrophysicists. Astrophysicists didn't worry about the distribution of mass in an expanding universe because it was not one of their concepts. The discovery of the electron in 1897 ushered in the modern age of observations at the atomic level, and the development of large-scale telescopes earlier in the 20th century started exploration of space and time on an extragalactic scale. These new observational skills have led us into domains where the behaviors of masses is not at all what we were expecting, both in the very small and the very large. And these new discoveries have, as of now, raised more questions than they have answered, even in the case of the ubiquitous electron. The concept of electric charge is as mysterious in its fundamental reality as the concept of mass. We have known since Benjamin Franklin's time that the charge comes in two matching forms, which we label positive and negative. A stationary charge gives rise to an electrostatic field that acts on other charges, and perhaps also on itself. A moving charge gives rise to both an electrostatic field and a magnetic field. A moving observer looking at a, to us, stationary charge sees both fields where we see just one. The nature of these electromagnetic fields, which can exist in a medium or in a vacuum state, has never been clearly revealed, nor has the nature of electric charge that generates them. We might think that there should be also a magnetic charge, but persistent searches have failed to find it. Chemical experiments in the 19th century made it clear that electric charge exists in a quantized form rather than as a continuous fluid of some kind. The identification of the electron by Thomson and others showed that it is a carrier of the unit charge, and that it might, in fact, simply be the charge. Electron scattering experiments carried out in the mid-20th century indicate that charge on the electron is concentrated in a very small area. In fact, it has no measurable size at all, down to the length of scale of 10 to the minus 16 centimeters. If this point charge is all that there is to the electron, then the large values observed for its spin, angular momentum, and magnetic moment are results for which we have no conventional explanation, since these values, if calculated from the standard formulas mechanism of electrodynamics, requires a length scale of roughly 10 to 11 centimeters. The puzzle about the actual size of the electron is compounded when we move to the other basic massive particle, the proton. The proton carries the charge, a positive, where the absolute value of E is precisely the same as that of the electron. The proton also has the same spin as the electron and has a magnetic moment. But unlike the electron, the proton has a finite electromagnetic size of about 10 to the minus 13 centimeters. The crucial point here is that the measured size of the proton is in fact roughly what we'd expect theoretically from the value of a spin, a magnetic moment. Why should the proton, with its classically scaled spectroscopy, be so different from the supposedly point-like electron with an inexplicable spectroscopy? This is really a question about theory more than experiment. The experimentally observed elementary particles have mass values that were not anticipated and are not understood. But we might expect that the theory, which gives us some guidance about spectroscopy of the proton, should do the same for the electron. And perhaps, as we suggest below, it might just do that, but with a required extension of our concept of mass. When we move the proton to quarks, the substates that make up protons and neutrons, the mass mystery becomes even deeper. When quarks were first postulated by Gell-Mann and Niemann, it was assumed that with enough energy we could knock a proton apart to its basic components. When this failed to happen, it was attributed to the fact that proton quarks are very massive and have large binding energies. When collision energies got very high and quarks still didn't appear, it became apparent that this was not the answer. A different type of bonding mechanism based on gluons was proposed, and the proton quarks themselves were now assumed to have very small masses, with almost all the proton mass arising from the quark-gluon plasma. Further mass mysteries awaited in outer space. Modern telescopes enabled us to examine large spiral galaxies in detail, and it became apparent that these galaxies do not contain enough visible matter to hold themselves together gravitationally at the observed rotation rates. They must have some kind of dark matter that is clumped in outer regions of the galaxy. Also, the existence of black holes is required in order to explain the tremendous energy outputs of quasars. A black hole is a massive burnt-out star that has collapsed to a small size under the action of its own gravity, and whose gravitational field is so strong that no light energy can escape from it. Another result of the Casimir effect demonstrated that if we hold two plates close together in a vacuum, there is an attraction between them that is generated by the ceaseless production of annihilation of charge pairs in the vacuum, the so-called zero-point energy. Thus, empty space is not really empty. Now, I get a couple questions here. And I guess they're going to get answered by the end of the book somewhere. But these black holes and dark matter and dark energy, so they're not necessary if you subscribe to the electronic universe model. And I still haven't seen anybody demonstrate how the Casimir effect is different than gravity. I mean, I don't see in the equations of a Casimir attraction the subtraction of the gravitational field that so what's the difference? I don't know, and I never had anybody explain it to me. I mean, I could just be simply missing something in the theory that why they don't why I don't know why Casimir effect and gravity are not related. But anyway, as we enter the 21st century, further refinements in our concepts of mass are being forced upon us. Neutrinos, antineutrinos are electrically neutral leptons, which are emitted. For example, a neutron muon tau decay, postulated and then identified in the 20th century. Neutrinos carry energy spin of 1/2 h bar and lepton number. Their interactions are so small that they can penetrate through 100 light years worth of lead bricks before they interact with the lead. It was originally believed that neutrinos are massless and travel at the speed of light. However, measurements of electron neutrinos fluxes from the sun indicated that only 1/3 of the expected events were occurring. Recent experiments have confirmed that electron neutrinos are being transformed into muons and tau neutrinos as they travel through space, which requires that they have finite masses. Since the universe is flooded with neutrinos, even a small neutrino mass causes them to make a substantial but not decisive contribution to the overall mass of the universe. So in other words, it's not going to make up for the so-called missing matter, which you don't need if you subscribe to electronic universe anyway. Perhaps the strangest modification in our concept of mass comes from modern cosmology. In the Big Bang Theory, the universe expanded from a point-like beginning to its present size, and observations indicate that it is still expanding. Space is filled with low-energy electromagnetic radiation from the original expansion. In order to explain the gravitational attraction that has created galaxies and clusters of galaxies, we have to assume the existence of large amounts of dark matter in space, as mentioned above, whose composition is a mystery. But in order to simultaneously account for the large expansion rate of the universe, we may also have to assume the existence of vast amounts of unobservable negative pressure dark energy. So, sometimes it's noted as quintessence, or the fifth essence. This postulated dark energy, whose composition is also a mystery, is thinly spread throughout the universe because it has the unique property that it repels itself gravitationally. Current estimates are that dark energy constitutes 73% of the mass of the universe, and exotic dark matter constitutes 23%. The ordinary baryonic matter with which we are familiar, protons and neutrons, is assigned just 4% of the matter of the universe, with only 1/8 of the amount appearing in visible matter. Thus, from this viewpoint, most of the space in the universe contains matter, energy, and forms that are completely unfamiliar to us. And that's why the guys with the electric universe have, totally done away with this ad hoc nonsense. But one familiar object, which also has puzzling mass properties, is the photon. The photon has a spin of 1, that is J equals h bar, and a circularity polarization photon beam can rotate a quarter wave plate. But the photon, unlike the neutrino, has no measurable rest mass, even though it carries energy and momentum. Since an energetic spin 1 photon can be converted into an electron-positron pair of spin 1/2 particles, the spin of the photon must, in some sense, be related to the spin of the electron. Thus, the models we make for these objects must be interrelated. A particle spin is, in principle, a spin angular momentum, which involves an extended mass rotating around a center. Hence, the mass problem energies in a very crucial way in the dual concepts of massless photon and point-like electron. In the present paper, we bring all the information we have about the spectroscopy of the electron to see what it can tell us about the structure of the electron. Many years ago, Albert Einstein, who spent years worrying about the structure of the photon and the structure of gravitational space, made the following observation. It would be sufficient to really understand the electron. Maybe he was, as usual, correct. Now, so this is kind of interesting. So if you have the electron and the photon actually as two parts of, of something that I guess, exists extra-dimensionally. Okay, here's the spectroscopic bulk size of the electron. The estimates of the spectroscopic size of the electron come from the magnetic moment and the spin angular momentum. Okay, so he's going to get into all the technicalities here. Relativistically spinning sphere, electron model. Let me see if there's anything else here that's sort of page 132. Okay, break. Okay. 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 Oh, that's where I'm reading to. Okay. All right. Relativistically spinning sphere, electron model. We demonstrated above the magnetic moment. Electron can be reproduced by a current loop of radius r, RC, which the charge E is rotating at the velocity of light. We also showed the mass of the electron is in the form of a solid sphere. The radius 5/4 of the radius times the speed of light. Then we can reproduce the spin of the electron by non-relative rotation of the sphere, where its periphery is moving at the limited velocity of light. However, the sphere, the rotating this fast, its rotation will be relativistic, and the mass distribution will be non-uniform. The sphere becomes heavier near the periphery, which increases its momentum of inertia and decreases its required radius of the sphere, thus bringing the spin radius more in line with the radius required for the magnetic moment. We can make this result quantitative relativistic equation for spinning ring of matter. Radius r. Okay, so this is kind of really interesting. A theory here where they're saying that if you have this, it'd be kind of like a spinning surface with a hollow inside. Okay. So let me see if there's anything else here that's okay. Mass of the neutrino. Let's read that here. This is. Let's see. Okay, here's what else is in here. They got models of some pretty interesting, pretty complex stuff though. Maybe I can show you that picture there. Let me see if I can get that in there. That's okay. These are, I guess, the points of charge and so forth, and it's like, it's pretty interesting. Anyways, zero rest mass photons and electron waves as particles whole in the Zeron excitations. Difficulties in understanding the nature of the electron mass are paralleled by even more difficulties in understanding the nature of the Debroglie electron wave. Moving electrons are accompanied by electron wave packets that clearly affect the motion of the electrons. What are these wave packets? Conventionally, they are denoted as mere probability distribution, mathematical constructs. But a physical system, such as a wave packet that does something, ought to be something, at least in the opinion of the present author, and myself included. I always said the probability wave is like the flying spaghetti monster, you know. The electron wave packet is much larger in size than the associated localized electron that emerges in the detection process. When the electron observes its wave packet, it collapses and vanishes without a trace. It is a zero rest mass entity. All moving objects, for instance helium atoms, produce similar particle waves whose frequency depends only on the object's mass and velocity and not on internal frequencies within the object. In addition to the massless particle waves, the only truly massless particle that we know about is the spin 1 photon that is created out of pure energy in atomic transitions or particle-antiparticle annihilation processes, and which give up its energy and angular momentum and vanishes when it is absorbed. Like the electron, the photon is accompanied by a wave, the electromagnetic wave, as it moves along. The analogy between photon-photon wave system and the electron-electron wave system are very close, and they both share the enigma known as particle wave duality, wherein the particle wave system behaves like a wave when it is moving along and like a particle when it is stopped and detected. In trying to determine the nature of massless particles and massless waves, we can employ two guidelines obtained from the above studies of the electron. The spectroscopy of the massless particle or wave, its frequency, energy, angular momentum, and internal charge states gives valuable information about the structure of the physical system involved. 2. The spectroscopic requirements may lead us to a new type of mass for the system. In the case of the electron, we demonstrated that its spectroscopic requirements can be satisfied within the confines of our own theories of mechanics and electrodynamics by invoking a new kind of non-interacting mechanical mass that, together with small magnetic self-energy, constitutes the rest mass of the electron in the case of the massless particle waves and photons. We will now show that the spectroscopic requirements can be met by invoking particle-hole excitations in the vacuum state, where the holes function mechanically as negative mass states and appear electromagnetically as electrically charged objects, in the same manner as the semiconductor hole states. We denote the particle hole pH pairs as zerons, since the P and the H contribute to the total energy, angular momentum, and charge of the pair cancel out, and since the pH excitations, which require, that's pH, by the way, particle hole, excitations, which require rotational motion to maintain their stability, vanish without a trace in the de-excitation process. Electron-positron pairs can be created out of pure energy, but are positive energy particles that require twice the energy of a single electron to create, and which release this energy when they annihilate. Which this is probably my favorite theory in this whole book so far. Yeah, this is Malcolm H. McGregor, Santa Cruz, California. This, I think, is making an awful lot of sense. And it's interesting because, see, he's not brushing things under the carpet like, excuse me, like, what's that guy's name? Krauss. I forget Krauss, that guy, that atheist is trying to say that, energy, a universe out of nothing. Okay, well, this idea of creation ex nihilo, out of nothing, is not biblical. It's not in the Bible. You won't find that in the Bible. The Bible never says that there's a creation out of nothing, because you had to have a pre-existing condition. And the preconditioning is God. And if you think God is nothing, and if you're going to add the universe to God, then God is not all powerful and all omniscient and all omnipotent and omnipresent before the creation of the universe. So there's a big change in the nature of God because there was an addition of a universe. And so that's just totally not there. And, and it bothers me that so many Christians are repeating this nonsense about creation ex nihilo. They didn't think it through. It's not. It's an insult to God, actually. If you think it through properly, you're adding something to God, and you can't do that. Now, I understand maybe what they're saying is there was no pre-existing matter, but there's nothing in the Bible also that indicates that there was ever a pre-existing condition of non-matter. Okay, so what happens is there's this confusion. The biblical model is you have finite, transient matter, the kind we experience because we're finite beings, and you have eternal matter. And that's God's realm. God's realm is the realm of eternal matter. That's always been the biblical model. And so this idea is that, okay, so you see you have the idea that Alison Krauss, the out of nothing guy, is suggesting is that the total sum energy of the universe minus gravity is zero, but that's just not true. It would work like this. Okay, it would work just like what this guy's saying here. Okay, the stability vanishes without a trace in the de-excitation process. Electron-positron pairs can be created out of pure energy, but are positive energy particles that require twice the energy of a single electron to create, and which release this energy when they annihilate. So really, if you're going to have a creation, a negative gravity and a positive gravity equation, your total energy is twice. It's not zero. So anyways, okay, now I'm going back to the book. Okay, if we think of empty space as being a total void, then it is not easy to envision the process in which a particle state is created, lifted out of the void, and leaves behind a matching vacancy denoted as a hole. What is the hole in? But if the so-called empty space is in fact some kind of residual mass, or if it represents a sea of zero-point excitations, as evidenced, for example, in the Casimir effect, then the hole represents a gap in this spatial continuum. As discussed above, recent astrophysical studies indicate the universe appears to contain large amounts of attractive dark matter and repulsive dark energy spread out over the vast regions of the space. The nature of these invisible mass states is completely unknown, but their possible existence suggests that our ideas about empty space may need to be updated. In this context, the concept of holes in the vacuum becomes more plausible. By using particles and holes to account for massless photons and massless matter waves, we may be able to examine the nature of the mass of the vacuum state on a microscopic as well as a galactic scale of distances. So this is, I really think this guy's on to something very important. The systematics of vacuum state particle Hall excitations have been given elsewhere, and we summarize the pertinent results here. The basic excitation, particle Hall excitations, the rotating xeron is displayed schematically. The left figure, the pH mass and charge together with the momentum vectors in the laboratory frame reference. The right figure show the equilibrium force of vectors in a rotating frame. That was those graphics I showed you before. The Debroglie wave equation is customarily used in the form of gamma equals h over mass times velocity. Okay. So this to me is rather ingenious. Now I got one question, one problem with it. And okay, the problem I'm going to have with this is, and it's not, it's not real. It's not going to take down the theory necessarily, but can you have a vortex in a vacuum? I don't know. See what it's really weird, because can you ever actually have a state of nothingness? See, his model still has this, the center of this, of this vacuum, this particle hole is not just, it's a particle hole in the 0-point background energy. I don't know if you can have a force that's strong enough to do that, and if there's such thing, because in that hole is, once again you come up across this this idea that just cannot exist, and that is you have a state of nothing in the center. I mean, I could see if it could definitely be, I don't know, maybe if because you have to have an extra dimensional substratum for what we experience as the universe. So maybe in our dimensionality there is a there is a nothing condition there, but I mean in the substrate underneath there has to be something. So anyway, that's my question with this. But all right, let's see. This is really the most interesting theory so far, I think. All right, the xeron rotation is dominated by large mass values. Their mass energies, angular momentum, essentially cancel out. Thus, they can be easily excited and de-excited. It is required for the production of electron waves. The choice of h bar over 2 for the angular momentum of P seems arbitrary in the case of the electron waves, but is more relevant in the case of massless photon. The irreducible photon basis state is a rotating xeron anti-xeron quartet, as shown in this Z minus Z bar quartet as particle-antiparticle symmetry. It accounts for spin angular momentum, h bar, transverse cross-electric and magnetic fields, and circular polarization of the photon. It revolves around the Einstein frequency, omega E over h bar, the overlapping h and h bar Hall states, which are held together electrostatically, play no role in dynamics but are important for the overall energy balance. The electromagnetic wave that accompanies the photon is closely analogous to the electron wave that accompanies the electron. Is logically constructed of single xeron and anti-xeron excitations. The xeron and anti-xeron particle Hall excitations of the vacuum state serve as the basis states that can be used to account for the main properties of the massless photon and massless electromagnetic particle waves. One of the key problems here is to reproduce large spin angular momentum, J over h bar, of the photon in terms of rotating masses, keeping in mind that the rest mass of the photon is zero. This clearly requires a pairwise use of positive mass and negative mass Hall states. The main goal in the present paper is to see what this tells us about the vacuum state rather than to focus on the particle properties of the photon. In order to create the xeron, we require a spatial manifold of negatively charged positive mass matter And in order to create an anti-zeron, we require another manifold of positively charged, positive mass antimatter. If we superimpose these two manifolds, we can envision that the negative potential energy of the electrostatic attraction offsets the positive energy masses, thus keeping the overall spatial mass density at a reasonable value. This is the rather complex spatial continuum that we require in order to reproduce massless photons with large 1 h-bar spin values within the context of our present spectroscopic theories. So this is really, I think this guy's really on to something. I think that's how you have to do it. You have to have, basically, I mean, it's kind of like the Dirac Sea, where, really everything is, just like a computer simulation, everything's made out of pixels. In this case, everything's made out of energy density differences in what you call voxels. And they have these characteristics that give rise to, in the same way that the different properties given to pixels give rise to images and movement. This is giving rise to three-dimensional images, inertia, masses, and so forth. This is really ingenious, and it's thoroughly enjoyable. Dynamics basis for the Debroglie superluminal phase velocity. In order to produce a large spin value for the otherwise point-like electron, we introduced a new type of mechanical mass that is required to be non-interacting and very rigid. Then, in order to reproduce the large spin value of the massless photon, we introduced particle hole pairs denoted as zerons and antizerons that have matching positive and negative masses. Since the photon travels at the luminal velocity of c in a vacuum, the sum of the pH positive and negative masses in the pH pair is required to stay finite at this velocity. When we use zerons to act as basis states for de Broglie electron waves, we encounter the additional problem that the zeron moves at a superluminal velocities. The de Broglie velocity relationship is V, capital V equals c squared, where V is the group velocity of the electron and V is the phase velocity of the electron wave. This velocity relationship can be derived by requiring relativistic invariance between the electron and its wave. It can also be derived requiring relativistic energy and momentum conservation in the excitation of zerons by moving electrons. This calculation has been published elsewhere, and we summarize them in here. I don't really have too big of a problem with superluminal phenomena. I think that, okay, here's my understanding is that if you want to give a ontological speed limit, speed of light, if you imagine reality being presented to us in sort of a, the old-fashioned 35 millimeter frame movie projector, and you have for each present state, you have to set the stage. It takes time to set the stage. Certain aspects of the stage cannot be set in that time limit. That's your C, and then there could be other things that don't require. There could be, the stage can be set because it's actually part of the substrate, and so you don't need to worry about the speed of light. Okay, anyways, mechanical masses and constituent chords. I think this is getting a little too technical. Let's try to keep it a little bit more, like just philosophical. Okay, let me see here. All right, let's read. We're going to the next one. This is the electron in a 3+3 dimensional space-time. Yeah, it's another one of these. It's kind of interesting. We review the basic features. Okay, this is Polo Laciani and Robert Mignani, Rome, Italy. Okay. Review the basic features of a model of the electron in a 6-dimensional space-time with 2 extra time dimensions. The electron is assumed to be a massless particle in this space, and it acquires a mass when considered in the usual 4D space-time. Its spin and magnetic moment are obtained by an effect of polarization, which gives rise in the three-dimensional temporal space to a helicoidal motion along the usual time axis with radius of the order of the Compton wavelength of the electron. In this model, chirality is nothing but the direction of rotation of the electron in the time space. It is also shown that a connection can be established between 6D space-time and the recently developed Kaluza-Klein-like formalism with the energy of the fifth dimension. Introduction: time and the electron. How many times? What is time? Many definitions exist, all very different ones from the other, from psychological to physical. For example, Ravali has analyzed the distinct roles that the notion of time plays in different scientific theories and found 10 versions of the concept of time, from natural time to no time, all used in natural sciences from physical point of view and in the framework of special relativity. Time is the fourth dimension of the Minkowski space-time, namely the component of the position of 4 vector. This reputation is so well established experimentally that a necessary requirement to be satisfied by a physically acceptable theory is its Lorentz covariance in a space-time with 4 dimensions and 3 space-like and 1 time-like. As is well known, there is no experimental evidence that time has more than 1 dimension in our universe. This is obvious since any matter with a different time direction would remain observable only for a very short time before disappearing almost immediately. For example, had particles been created during the Big Bang with more than 1 initial common time direction, they would have been immediately separated, and now only those with the same time would constitute our universe. The hypothesis of Stuckelberg and Feynman. The antimatter corresponds to particles traveling backwards in time, and can explain why the universe does not seem to contain some amounts of matter and antimatter. But I was thinking about that in the previous model, what causes the electron to wave, the particle whole thing. That does a good job of putting antimatter in the background, but necessary. So it's not this that is annihilated. It's not this idea that, is so much annihilated and for some reason there was a slight amount of more matter than antimatter. that model goes away if you put the antimatter in the background like the previous model did. I like that. However, space-time is a physical concept, then not only a mathematical representation as suggested by Einstein's special relativity. The question arises, why do 3 space coordinates and only 1 time coordinate exist? The idea of multidimensional time was considered in the second half of the past century mainly as a possible tool to explain quantum features in a semi-classical framework. In particular, the problem of a possible symmetry in the number of dimensions in space and time was noticed in the early 70s in the framework of the generalization of special relativity faster than light speeds. Indeed, the superluminal Lorentz transformations in 4 dimensions introduced by Racimi, one of the present authors, changed the sign of the space-time interval, thus mapping space-like dimensions into time-like ones, and vice versa. This leads to a natural way to the hypothesis of the equal number of time and space dimensions, following Demers, who assumed a 3 plus 3 space-time and applied it to some aspects of trichromatism. Magnani and Racimi introduced a time vector besides the space vector in order to explain the appearance of the imaginary quantities entering into the 4D generalization Lorentz transformations. The space-time point in space M33 is therefore represented by a 6 vector. In agreement with Demers, it was assumed that only the modulus is physically observable for bradyons, slower than light particles, whereas the modulus looked like the R vector is a meaningful quantity for tachyons faster than light particles. Okay, this gets pretty complex pretty fast. Recall space-time with more than 4 dimensions have often been proposed mainly in attempts to unify fundamental interactions. The first pioneering proposals due to Kaluza and Klein, they introduced 5-dimensional space-time in order to unify gravitation and electromagnetism in a single geometrical structure. Their scheme, in which the coefficient of the fifth coordinate is constant, was later generalized by Jordan and Thury, who considered this coefficient to be a general function of the space-time coordinates. The Kaluza-Klein formalism was later extended to higher dimensions and also to the hope of achieving unification of all interactions, including nuclear weak and strong forces. Modern generalization of the KK scheme require a minimum of 11 dimensions in order to accommodate the standard model of electroweak and electrostrong interactions. Note that 11 is also the maximum number of dimensions required by supergravity theories. For a recent exhaustive review of Kaluza-Klein theories, we refer to the reader to an excellent monograph by Wesson. In the models, these extra dimensions are all space-like and are not observable because they are warped up in a very small region. Compactification of dimensions, compactified dimensions. I never liked compactified dimensions. I think that's backwards. The dimensions would actually not be compactified, but would be outside in a sense. They would be above, and not they would be. That's how I would say that if you got these extra dimensions, we're inside of them, not the other way around. I think that makes a lot more sense. What is the electron? The electron, discovered by J.J. Thomson in 1897, is the first and best known elementary particle and plays a fundamental role in many observable physical phenomena. Notwithstanding, it still remains an enigmatic object. Its intrinsic features like mass, charge, spin, and magnetic moment have been measured with a very high level of accuracy. Only electron size is still unknown, since many different values from 10 to the minus 11th to 10 to the minus 16th centimeters can be attributed to its radius depending on different phenomena under consideration. All the electron properties related to its interactions are well described in the framework of the Glass-Howell-Weinberg-Salim electroweak theory. However, the values of the mass of the electric charge and the electron considered in the quantum electromagnetics are not intrinsic, but result from interactions with the vacuum. As a matter of fact, there exists presently no model of electron able to fully account for its behavior and features in a convincing way. The above facts are well known and generally accepted as a consequence of the impossibility of describing the electron either classically or quantum mechanically. This leads to quite contradictory view that the electron is regarded as an electrically charged point-like particle, but endowed with an unknown internal structure responsible for the spin and magnetic moment. The situation already summarized by Fermi in 1932 was restated by Barat 1990 in the following terms: a spinning particle is not quite a point particle nor a solid three-dimensional top. What can it be? What is the structure which can appear under probing with electromagnetic fields as a point charge, yet as far as spin and wave properties are concerned, exhibit a size the order of the Compton wavelength? Although most physicists believe the quantum theory explains everything that can be explained concerning the electron, many attempts have been and are being made to establish a model electron able to link together its static and dynamic properties. Several models of electron have been proposed. They can be divided roughly into 3 classes, in which electron is regarded as strictly a point-like particle, an actual extended particle, an extended-like particle in which the positron and the point-like charge, an extended-like particle in which the position of the point-like charge is distinct from the particle center mass. And another type of theoretical approach, a generalization of the theory of relativistic spinning particles, we may cite the following. Classical extended electron theories that use the Lorentz-Dirac equation to derive information on the electron's experimental behavior from parameters of its internal structure. Classical mechanical models, the electron as a rigid rotating sphere with a point-like equatorial electric charge. The electron is a point particle buffeted around so that it is actually position is spread out over the region of space vastly larger than the intrinsic size of the electron itself. This motion corresponds to the Zitter-Bewegung of QED, which is like a kind of like a like Brownian motion. Okay, explains the Lamb shift in the atomic nuclei and is the basis for most recent studies of the electron model, in particular if the trajectory of the electrically charged particle is a helix around the center of mass that moves like a relatively spinless point particle, and oscillatory motion gives rise to the spin. Okay, that's pretty interesting. Okay, is there a connection between two seemingly unrelated problems, namely the number of time dimensions and a consistent model electron? We discussed above, the answer might be yes. Indeed, recently, one of the present authors proposed that a model of the electron and the other charged leptons in a 3+3D space-time. In this framework, the electron is assumed to be a massless point particle subject to attractive field towards the space-time 3.1, a 3+1 space-time. This attractive force is caused by a vacuum polarization arising when the charged electron is removed from the standard space-time. The electron trajectory in the time-space, as seen in the electron rest frame, turns out to be a helix with our usual time axis and radius equal to the Compton wavelength. The electron's motion along the time axis occurring at the speed of light creates an arrow of time. Obviously, since only 4 different time motions are allowed, corresponding to 2 time directions and the 2 directions of rotation, a 4-Compton wave function is required in order to describe the motion of the electron in the usual 4D space-time. This model exhibits some interesting features, among which it recovers the usual values for the spin magnetic moment of the electron. Quantization of electron mass follows from the existence of a discontinuity of attractive potential, and the time energy uncertainty principle is recovered indirectly. In this paper, we shall review the 3-time model of the electron, and we will also show possible connections with the 5-dimensional formalism, energy as extra dimension. The content of this paper is as follows. The model of the electron in a 6D space-time reviewed in section 2. The foundations are given in the subsection in 2.2. It is known that the electron mass is derived as an integration constant from the Klein-Gordon equation for a massless particle in 3+3 space-time. The usual values of the spin and magnetic moment of the electron are obtained from the hypothesis of an attractive force caused by the vacuum polarization. We show in section 3 that time spin of the electron can be identified with chirality. In section 4, we establish the connection between the 6D space-time decludes a Klein-like formalism with the energy 5th dimension. And 5 concludes the paper. Let me see. I got some notes on where the most interesting parts of the book are, but they're all over the place. Let me see on page 169. Okay. I'm kind of finding the interesting stuff as I go. I wandered from my notes. The model of electron is a particle moving in space with three space and 3 time dimensions, has the foundation of the following considerations. The existence of spin, and therefore the magnetic moment of the electron, can be associated with 2-dimensional motion. This motion cannot be interpreted as the spinning of an electron in ordinary space, must therefore be thought of as motion in an internal space, or in 2-dimensional additional to the standard 3+1 space. In the latter case, these 2 extra dimensionals cannot be space-like due to the behavior of the Coulomb force. The simplest hypothesis, therefore, is to assume the extra time dimensions. The modern view of the problem of the electron mass, pioneered by Wheeler and Feynman, assumes that it is not electromagnetic origin, as stated by Abram, Lorentz, and Poincare classical model of the electron, but entirely mechanical. In this case, however, the rest mass of the electron must follow from its equation of state and not be added to by hand by an external parameter. This contradiction can be overcome by assuming that the electron is a massless particle, which acquires mass by means of a suitable mechanism, an assumption made in the past by many authors. Conservation of electric charge holds strictly in the usual 3+1 space. As a consequence, if for any reason a charged particle leaves the standard space-time, the resulting vacuum polarization acts strongly on particles itself in the form of an attractive force which attempts to restore the original condition by bringing the particle back into the starting space-time point. Let me see if... Oh, okay, excuse me, I got an important call. Okay, let me see. Whoops. I'll have to call him back. Let me text him. So, at any rate, this is another interesting one that parts of the parts of the electron are derived from either extra dimensions and this sort of substratum of 0 point background, which I like. I think that's where you got to go. I don't think that I don't think that you're going to get the answers with just a simplistic three-dimensional space-time. I don't think that's possible. I think that just like the nature of the origin of the universe requires a pre-existing condition of an intellect, is what we call God. I mean, I have no problem with that. Yeah, so I'll see what else is interesting on this particular. I'm texting my friend, making a video. Making a video will call back. I got my flip phone here. I love it. I never got a smartphone. I got flip phone technology, baby. Okay, and they charge me to send text messages. That's great. I like to keep up with the latest technology. Okay, so I think that this is a viable explanation. I like this one too. Yeah. Okay, let's move on to the next one. Can studying the inertial and gravitational properties of the electron provide us with an insight into its nature? Veselin Petkov, Montreal, Quebec, Canada. It has shown that both the classical spherical electron and the point-like electron considered in the framework of quantum electrodynamics predict the correct form of the expression of the inertial and gravitational forces acting on non-inertial electrons. Surprisingly, the two models turn out to be indistinguishable if formulated in terms of a radically new idea of the electron structure, which explains why the correct forms of the expressions for the inertial and gravitational forces can be derived from the two models. That idea also appears to shed some light on the number of quantum mechanical puzzles. Okay. Introduction. Studies of the nature of the electron deal, as a rule, with the quantum mechanical features. This paper takes a different approach. In Section 2, the inertia and the gravitation of the classical electron are discussed. The classical model regarding the electron as a small charged sphere leads to the correct expression for the inertial force acting on an accelerating electron and for the gravitational force acting on an electron at rest at a gravitational field. As these forces originate from the interaction of different elements in the charged sphere representing the classical electron, it is concluded that their derivation from the classical model is an indication that the real electron is unlikely to be a point-like particle of a size smaller than 10 to the minus 18 meters, as experiments probing its scattering properties appear to suggest. In Section 3, the inertial and gravitational properties of the electron in terms of quantum electrodynamics are studied. It is shown that a point-like model in the electron in quantum electrodynamics yields expressions for the inertial and gravitational force in which the forces are proportional to the acceleration and mass of the electron. Section 4 analyzes arguments that indicate the electron cannot be a point-like object and considers a model of atomism in which appears to resolve several puzzles. Why is an electron not localized when not measured? The stability problem of the classical electron. The meaning of the scattering experiments according to which the electron appears to be a particle localized in an area of dimensions smaller than 10 to the minus 18 meters, which contradicts the wave-like nature of the electron. And 4, why do both the classical electron and point-like electron in quantum electrodynamics lead to the correct forms of the expression of the inertial and gravitational forces acting on a non-inertial electron accelerated and supported in the gravitational field, respectively? It is also shown that the last section that the 4 atomistic model of the electron may shed some light on a number of difficult quantum mechanical problems. Inertia and gravitational properties of the classical electron. In the classical model of the electron, its charge is uniformly distributed on a spherical shell. This model offers a mechanism responsible for the electron's inertia and mass. The repulsion of the charge elements of an electron in a uniform motion cancels out exactly. There is no net force acting on an electron. If, however, the electron is accelerated with respect to an inertial reference frame, its electric field distorts, which causes the repulsion of its elements to become unbalanced. As a result, the non-inertial accelerated electron experiences a self-force that resists its acceleration. It is precisely this resistance that we call inertia, why repulsion in the different parts of an accelerated electron becomes unbalanced, as explained elsewhere. Okay, this is pretty interesting. The guy's going pretty far, classically. The calculation of the self-force is easier in the non-inertial accelerated rest frame in which an electron is at rest. At first it appears that the field of the electron is not distorted since it is at rest, which would mean that no force is acting on the electron. If this were the case, there would be a problem. An inertial observer and a non-inertial observer would disagree on whether or not the electron is subjected to a force. As the existence of the force is an absolute fact, all observers should recognize it. This problem disappears when a corollary of general relativity, that the average velocity of light in a non-inertial reference frame is anisotropic, is taken into account in the calculation of the electron field. The average isotropic velocity of the electromagnetic disturbance. Okay, the property of acceleration is a radius vector representing the path of light signal between the 2 points separated by the distance r. The isotropic velocity of light causes the distortion of the electron field of the electron. As a result, the balance of mutual repulsion of all parts of the charged elements of the spherical shell representing the classical electron is disturbed. There's resulting net force. So let me see. Okay, you know what? I think this is getting long enough. I'm going to call my friend back, but we will continue this video. It's I got to get out and get some sunshine. But remember, we'll be continuing this shortly. What is the electron? Maybe I'll do the next 2 parts during this weekend. I'll stop now. Thanks for listening, and we'll talk to you later.